So let me introduce my postdoc, Dr. Jicheng, from Wayne State University. In fact, he started in my lab during the COVID-19 last year. He was supposed to join the lab in March, but then the nationally shut down. So eventually he joined the lab in April in 2020. And that we still haven't opened the lab there, but he's very fantastic, during that time. They helped me to do on the docking that we think about a couple of projects for the heparanase inhibitor and then COVID-19 inhibitor. And even right now, we're working on the p-tau project for Alzheimer's disease. So even in the short time in the lab, he is very, very productive. Actually, he got a PhD from Michigan State University, Su Fei Huan, and then joined my lab. And today he will focus only on this project of how we systematically study the sulfation pattern on oligosaccharide to modulate heparanase activity. And then we see the effect of the linker to improve the activity. And then this is the only one of his projects. And he probably had two other projects going on right now, as I said, on the COVID-19 and then for the Alzheimer's disease. Now the floor is for you, Jicheng.
Thanks for the introduction. So today I'm going to talk about the project trisaccharides with specific sulfation sequence in modulating hyperlase activity. So hyperlase is an endoglycosidase in remodeling the extracellular matrix and thereby in regulating the biological activities. So translation of hyperlase mRNA on ER to lead on the synthesis of pro-hyperlase on Golgi apparatus and then secretion to the extracellular space. So there are two roles for the pro-hyperlase. First, it can interact with hyperlase binding protein and receptor on the cell surface, resulting in increased expression of growth factor and tissue factors, which can promote cell proliferation and tumorigenesis. And second, it also internalized to form the active hyperlase. So the active hyperlase may translocate into the nucleus or secreted into the extracellular matrix. So once the active hyperlase released into the extracellular matrix, it can cleave the heparan sulfate and also release the heparan sulfate bound growth factors and cytokines, which can promote cancer cell growth and metastasis. So heparan sulfate is a polysaccharide. So I will show you in a second the structure of the heparan sulfate. And also the cleavage of heparan sulfate degrades the structural integrity of the extracellular matrix, permitting malignant cells to enter the bloodstream and metastasis. So we know the hyperlase, we know the heparin is the substrate for hyperlase. So heparan sulfate is also is a member of glycosaminoglycan family and comprise of disaccharide repeating units of glucosamine and uranic acid. So here the uranic acid, it could be glucuronic acid or it's carbon 5 isomer, iduronate acid. So N and 6O on the glucosamine and the 2O on the glucuronic and the uranic acid could be sulfated. Also, we could have rare 3O sulfation. So we know the heparan sulfate is a substrate, and the cleavage site is this 1,4-base linkage between glucuronic acid and the glucosamine. So in 2015, Professor Davis' group at the University of York published the crystal structure of human hyperlase. From the crystal structure, we can see hyperlase is made of 2 subunits and comprise 2 domains. So here is the binding cleft. It's about 10 angstrom and including the previously reported catalytic residue glutamic acid 343 and 225. So from the structure of the heparin sulfate, you see there are many sulfate groups. So the sulfation pattern could be important for the heparanase recognition. In 2015, the paper, they also study the binding with the substrate. So they use heparin sulfate oligosaccharide, and they found the minimum requirement is a trisaccharide unit. So here they also found the 6O sulfate and N sulfate on the -2. Those are important for heparanase recognition. So here they use the minus sign and the plus sign to label the subsize. So the minus is from non-reducing end and the plus is from the reducing end. And the cleavage site here is the beta 1,4 linkage is between the -1 and the +1. So at +1 and the -2, we have glucosamine, and the -1, we have the glucuronic acid. And besides that, they also found the 2O sulfate group on the glucuronic acid cannot be tolerated due to the steric effect. So those papers provide some insights on the binding with heparanase, but still there are some ambiguity remains. So here we look at the trisaccharide structure at the -2 and the +1, we have the glucosamine, and both nitrogen and the 6-oxygen could be sulfated. And the question is which sulfation is important. And also, we know the 3O sulfate group is important for the anticoagulant activity. So how about for the heparanase recognition? And we also want to confirm the 2O sulfate group on the glucuronic acid. And using the organic synthesis, we could change the anomeric configuration at the reducing end and to see if that's gonna affect the binding affinity. So based on those interests, we designed a library of different trisaccharides. So the synthesis starts with monosaccharide building block preparation. So here we prepare different glucosamine for -2 and the +1 subsites. So the PNB and NAP group we use for later carbon-6 or carbon-3 sulfation. And the AZ and the N-benzidine can be converted to free amine and for later selective sulfation and acetylation. So due to the limited time, I won't show you every single steps. So here with those monosaccharide, we successfully generate the disaccharide using NIS and a silver triflate promoter system. And the benzidine acetal could be removed by treatment with 80% acetic acid at 80 degrees. And the 6O hydroxy group can be selectively oxidized by TEMPO and BAIB, and the resulting carboxylic acid protected as methyl esters. So with those disaccharides in hand, we repeat the glycosylation and follow the deprotection and sulfation sequence. We successfully generate a library of 11 trisaccharides. So, and with those compounds in hand, next we so here I'm going to show you the list of those trisaccharides. So this 1-alpha and 1-beta, they are structurally similar to nitro heparin sulfate substrate. And we use those as a model substrate for comparison and the determination of the anomeric configuration in modulating the hyperanase activity. So 2-alpha and 3-alpha, we can determine the relative importance on the 6O sulfate. 5-alpha and 6-alpha, we replace one N-sulfate with the N-acetyl group. And the 8-alpha and 9-alpha, we can see the importance of the O3 sulfate group. 7-alpha, we made a highly sulfated compound. And for compound 4-alpha, we test the importance of the 2O sulfate group. So with those compounds in hand, we test the hyperanase activity using time-resolved fluorescence resonance energy transfer TR-FRET assay. So in this assay, we use heparan sulfate polysaccharide as a substrate. And on the heparan sulfate, we have both fluorescence donor and fluorescence acceptor. We mix the substrate with our compound and the enzyme hyperanase. So if our compound is a very potent inhibitor, the hyperanase and the heparan sulfate polysaccharide will stay intact after incubation. Then we will see the strong fluorescence energy transfer from the donor to acceptor. So we will absorb strong fluorescence intensity. So here we for compound 1 alpha and 1 beta. So 1 alpha shows very good inhibitory activity with about 390 nanomolar IC50 value. By changing from alpha to beta, we see the beta one is the worst in the table. So this is the first time we see the anomeric configuration at the reducing end can modulate hyperanase activity. So next, we confirm the 6O sulfate group is important. And also the 6 sulfate group at +1 glucosamine has a greater effect. So for the N-sulfate group is also important for the activity. So we replace one N-sulfate group with N-acetyl group, and we reduce about 30-fold potency. So for the 3O sulfate group will reduce the activity significantly. And for the highly sulfated trisaccharide, so we may think with more sulfate group, we should have higher activity, but here it doesn't, the highly sulfated compound didn't prove to be advantageous. So finally, with compound 4 alpha, so 2O sulfate group on the glucuronic acid cannot be tolerated. So we confirm that, so the compound shows very low activity. So here we can see compound 1 alpha is our lead compound. But by changing the anomeric configuration, we got the worst compound in our series. So next, we want to study the effect of the anomeric configuration. So we did docking and molecular dynamic simulation for those two compounds. So here, from the docking, we can see the N-sulfate group on the linker for compound 1 alpha form the hydrogen bonding with lysine 231. And here for the 1 beta, it forms hydrogen bonding with arginine 272. For both trisaccharide, the -2 N-sulfate formed hydrogen bonding with glycine 389, and N-sulfate group at +1 subset formed the hydrogen bonding with glutamine 270. So for from the molecular dynamic simulation for compound 1 alpha, so we are looking the distance between the CCO bond with those two catalytic residue. So glutamine 343 and 225. So here the glutamic acid 225 is a proton donor. For compound 1 alpha, we can see the distance is very steady. So the glutamic acid 225 formed the hydrogen bond with the +1 6O sulfate, and we didn't see any hydrogen bonding between the oxygen on the CCO bond. However, for the compound 1 beta, we do see the distance fluctuate. So glutamic acid 225 did form a hydrogen bonding with the oxygen on the CCO bond. So this compound 1 beta is likely to be hydrolyzed by the hyperanase enzyme, and the 1 alpha could be a good inhibitor. So after that, we did some Crossbow activity test. So here, first we tried the anticoagulant activity. We know that heparin is a very good and is a very good anticoagulant drug. So here you can see as the concentration of heparin goes higher, and we see the we see the inhibition with the coagulation factors. But for our compound, we can see there's barely any effect with those active factors. So next, we test the binding with platelet factor 4. So platelet factor 4 is responsible for causing thrombocytopenia. So compared to heparin, our compound shows very less binding affinity to platelet factor 4. So now we have our lead compound trisaccharide 1 alpha shows very good binding affinity to hyperanase. So next, we want to improve the potency. So here, from the library, we know the structure and the sulfation pattern has good results. So we thought we could change the linker part. So we choose the aryl acid as a linker because aryl acid and its derivatives already show the anti-tumor, anti-cancer, and anti-diabetic activity. And also it's a lipophilic linker. So as reported before, the lipophilic linker could improve the pharmacokinetics. So follow the similar synthetic route, we successfully generate both 21 alpha and 21 beta containing the aryl acid. Based on the hyperanase inhibition assay, this time we got a different result. This time the beta one shows much higher potency than the alpha one. So the beta one even shows twice more potent than our previously lead compound 1 alpha. So we did a preliminary docking study to look at the compound. So here is the binding cleft. For the beta one, we can see both aryl acid and the trisaccharide, they are in the binding pocket. However, for the alpha one, the trisaccharide is not in the binding cleft. So that's the reason we think why the 21 beta shows very high potency. So we are going to continue with the trisaccharide 21 alpha and the beta to test the cross-Bell activity. And more importantly, we can change the lipophilic linkers. So especially for this dexamethasone. So dexamethasone already show activity against the COVID-19. So we think if we can apply this linker to our trisaccharide, maybe we can test the compound against the spike protein. Thanks for Professor Nguyen to give me the opportunity to present the research, and thank you for our group members and the funding, and thanks for your attention.